Donsker's theorem gives us an effective way to simulate and visualize the paths of Brownian motion. They're random walks with time and space rescaled in different scaling regimes, time the square of space as the spacing goes to 0. And as we've seen, that produces paths that look quite rough, although they are continuous. In fact, Holder alpha continuous for every alpha less than 1/2, as we already proved. Let's see if we can measure precisely how rough they are. In the next 2 lectures, we will give some precise statements of path regularity and path roughness. And we'll start with variation. Let S be a normed space, and let omega, again doing double duty now, denote a continuous path on a compact time interval. We're going to define a notion of regularity for these paths that resembles some of the constructions from Riemann-Stieltjes integration theory. We will use partitions of the time domain. So let pi denote a interval partition of the time domain. That is, it's a finite collection of times from 0 up to t. Canonically, we let t0 denote 0 and tn denote capital T for our parameter n. The set of all such partitions will denote script p of the time interval from 0 up to t. Now, given such a partition, the pVariation of our path relative to that partition is the following quantity here. We take the increments of the path for that partition, that is omega of tj minus omega of tj minus 1, the little displacements corresponding to those small time intervals, and we measure those in LP norm, although these are just deterministic constructs right now. So all we're doing is taking the norm in the normed space of that increment. Usually we'll be thinking of paths in Euclidean space, and so this is just the Euclidean length of that displacement, taking its pth power and summing that up over the whole partition, and then taking the pth root of that. So that's the little LP norm in Rn. Now that, of course, depends on the partition that we choose, and so the pVariation of the path in general is the supremum over all possible partitions of that pVariation on the partition. Of course, that supremum might well be infinite, and is much of the time, as we'll see. But let's first look at some examples where it's finite. Suppose that we have a Lipschitz path, which of course means that any increment, omega of t minus omega of s, is controlled by some constant, the optimal such constant being denoted the Lipschitz norm, times t minus s. Well, if that's true, we can estimate the p equals 1 variation of our path as follows. v1 of pi and omega is defined to be this sum here, and by the Lipschitz condition here, that means that each one of those terms is less than or equal to the Lipschitz norm, which I'll therefore bring outside the sum, times the sum of tj minus 1 in absolute value. But of course, those are ordered, so that's just tj minus 1. Now that is a telescoping series. And so it adds up to just tn minus t0, which by convention is capital T. And so that is, of course, finite. And it's finite independently of the partition. So we find that in this case, the 1 variation of our path is less than or equal to that quantity there. And so the 1 variation is finite. We denote the set of paths that have finite 1 variation, BV, the bounded variation paths. And what we just showed is that the Lipschitz paths on 0t are contained in the bounded variation paths for any normed space S. To give some context and intuition for these Lipschitz versus bounded variation paths, let's consider the special case where the normed space is the real line, in which case we can talk about functions that are smoother even than either of these cases. Let's take a C1 function on the interval from 0 up to t. Well, if you look at this definition here of the one variation, so with p equal to 1, this looks an awful lot like a Riemann sum, and in fact it is. And it's not hard to show that in this case, the one variation of our C1 path is the integral of the absolute value of the derivative. Now there is a subtlety there about the definition here being the supremum versus taking a certain kind of limit, which we'll address in a few moments. But in this one variation case, this is correct. On the other hand, the Lipschitz norm of a C1 function is the maximum of the derivative. And so we see that comparing one variation to Lipschitz is like comparing an L1 norm to an L infinity norm. Here we're on a finite measure space, and we know that L infinity is therefore contained in L1, in fact strictly, and the same is true here. Indeed, in general, for a metric space S, these Lipschitz paths here are strictly contained in the bounded variation paths. Now, what about variations with p greater than 1? Well, in fact, it is perfectly possible for a path to have unbounded variation, for v1 to be infinite, but to have finite p variation for some larger p's. One thing that is true, though, is that if you ever get a finite variation at order p, then you'll have finite variation for all q bigger than p as well. And that is because for any fixed path, omega, on a compact time interval, the function of p, that is the p variation of that path, which is a function taking values in the positive or infinite numbers, is a decreasing function of p. So if it's ever finite, then it will stay finite for all further p's later on. To prove that, we're just going to prove that for each fixed partition of the interval from 0 up to t, the function that maps p to the p variation of the path on that partition is a decreasing function of p, and you can therefore take the supremum over all partitions of both sides of the inequality that this tells you comparing p to q to get this statement here. Now, to see that this is true, we just note from the definition of p variation right here that this is nothing but the little LP norm of a certain vector in Rn, and so it's going to suffice to prove that inequality for such vectors. That is to say, if we fix aj from 1 up to n, in the case that we're interested in, aj is just the norm of the increment of the path corresponding to each interval of the partition. And if p is less than q, well, that means that q can be written as p plus r for some r strictly greater than 0. And now if I take the LQ norm to the qth power of that vector of a's, well, I can write that as the sum of aj to the p times aj to the r. And now what I'm going to do is take that aj to the r outside the sum. Of course, I can't do that because it's indexed by j, but what I can do is take the maximum outside the sum. So this is less than or equal to the maximum over all I, those finitely many I, of ai to the r, times the sum of just aj to the p. Now I want to get everything in terms of p here, and I'll just note that the maximum of the ai, which are positive numbers, is the same as the maximum of ai to the p, all to the power 1 over p. And using that, we have that this is equal to the maximum over I of ai to the p, all to the r over p, times the sum of aj to the p. And now we'll make the blunt estimate that the largest term of all of these ai to the p is less than or equal to the sum of all of them, since they're positive. And so we have that this is less than or equal to the sum over all I of ai to the p, all to the power r over p, times the sum over all j of aj to the p. And now we can combine those. These two terms here are the same, and so this is equal to that sum of aj to the p, all to the power 1 plus r over p. But 1 plus r over p, which is p plus r over p plus r is equal to q. And so that's q over p. So this is the sum of the pth powers to the power q over p. And now comparing these two that I get at the two sides of the inequality and taking qth roots exactly tells me that the qth root of this is a decreasing function of q, which is exactly what we wanted to show. Now, going back to the one variation, as we noted before, it looked like there was a relation to Riemann-Stieltjes integration. And there is there, particularly because there is an alternate way to write the definition of the one variation, as follows. In the p equals 1 case, the one variation, which remember is defined to be the supremum over all interval partitions of the one variation on that partition, can be written instead like this. It's the limit as n goes to infinity of the one variation along any sequence of partitions, pi n, with the property that they are nested. That is, all the partition points in pi n are in the partition pi n plus 1, and then maybe there are some extra ones. And the mesh of those partitions, which is defined to be the maximum of the width of the intervals in the partition, goes to 0. Those are exactly the kinds of limits that come up in Riemann-Stieltjes integration. The reason that we have this alternate formulation here for the one variation is the following observation. If I have two interval partitions with one contained in the other, then the one variation of the smaller partition is less than or equal to the one variation of the larger partition. If I add more points, I will only increase the one variation. And to see that, let's take our smaller partition pi, like this. And if pi prime is an interval partition that contains all the points in pi, well, since both of these are finite, that means that I can get from here to here by adding points in sequence. And so, from an induction argument, we'll be able to prove this if we can prove it just in the special case where pi prime has one extra point. And just to save notational difficulty, let's decide that that point is actually in between t1 and t2. Then we can just compute that the one variation of the path along the partition pi, well, let's write it out. That's the sum of the increments in norm And now we just note from the triangle inequality for the norm that this term here is less than or equal to the increment from t2 down to t1 prime plus the increment from t1 prime down to t1. And the sum of all of those terms plus this one, that's exactly the definition of the one variation along p prime. That's why there's a good connection between one variation and Riemann-Stieltjes integration. In fact, the bounded variation paths are precisely those paths that can be used as Riemann-Stieltjes integrators. Just recall briefly that the Riemann-Stieltjes integral of a continuous function with respect to an integrator omega is defined like this. We take any interval partition of our interval from 0 up to t that we started with. We look at the increments of our integrator path along that partition, and we sum those d omegas up against the function on some other points if we like, where those other points are chosen in between the partition points with impunity. Now, if this omega was a non-decreasing continuous function, then the Riemann-Stieltjes theory told us that no matter what sequence of partitions we choose, as long as they're nested and have mesh going to 0, this will converge for any continuous function here to a consistent value, no matter how we choose these points. And we don't even need continuous functions here. There's a much wider class that will work. Now, we might be interested in integrating against integrators that are not positive, meaning that the path omega doesn't need to be increasing, but we can't just do it with any old continuous function, because that same theorem that this limit will exist simply won't be true. There are cases, especially if you continue on in stochastic calculus, where you might get a finite value for this limit for any choice of partitions, but the value will depend on what partition points you choose. If we want this to work exactly the same way, then it turns out what you need precisely is that the integrator be a path of bounded variation. And just for those interested in thinking about this further, in the case that the normed space is the real line, there is a nice description of exactly what the bounded variation paths are. They're precisely those functions that can be expressed as the difference of two non-decreasing paths, which is why they match up so nicely with the Riemann-Stieltjes integration theory. Now, what about p-variation for p larger than 1? Well, all of this is out the window. This characterization here does not hold true for p bigger than 1. In fact, it is perfectly possible for this limit over here, in the case of p-variation, to be finite for some particular p greater than 1, but for the p-variation to be infinite. And the reason that's possible is that this lemma fails to be true here. The precise application of the triangle inequality that we used here will not work if we have pth powers and pth roots involved. To see more concretely how that can fail, let's talk about a very closely related quantity, not the 2 variation, but the quadratic variation. If omega is a continuous path in a normed space S, and pi is an interval partition of the interval from 0 up to t, then we define the quadratic variation of the path along that partition pi to simply be the 2 variation squared of that partition. So just to remind you, what that means is that we're taking the sum over all the partition points in pi of the increments normed squared. Okay, so far we're just squaring the 2 variation for a partition, and now we know if we take the square root of that and take the supremum over all partitions, we get the 2 variation. Of course, we could take the square root outside the supremum as well, if we like. But instead, let's do the Riemann-Stieltjes type thing here. Let's take this quadratic variation on each partition and define the quadratic variation of the path omega, independent of partitions, to be the limit of these quadratic variations over any sequence of partitions whose mesh tends to 0. Of course, there's no reason to think in general that that limit will even exist, and maybe we have to be a little careful about which kinds of sequences of partitions we can use here, but I just want to note that in general, this, even if it exists, will not be the same as the square of the 2 variation, which, remember, is the supremum over all partitions of the square of the 2 variation on that partition. And these two are not going to be the same because of the fact that that lemma about interleaving partition points only increasing the variation doesn't work for 2 variation. For example, in the p equals 2 case, we can see explicitly how that can fail. If I take 3 times r less than s less than t, and look at the increment squared, omega t minus omega of r in norm squared, well, I can write that as omega t minus omega of s plus omega of s minus omega of r, quantity squared. And now if we wanted to employ that same lemma, we'd need to show that that's less than or equal to this. But in fact, what it is exactly equal to is this sum of the squares of those 2 increment norms plus twice the inner product between them. I'm assuming that the norm space is an inner product space when I do this, which is certainly true of the interesting case that we usually consider Euclidean space as our state space. Now, of course, for any particular path, this inner product here, it could be greater than or equal to 0. It could even be equal to 0, in which case we would get equality of these two things. But it could well be less than 0 as well. It's perfectly possible to find paths where this, at least for some times, is less than this. And that is why this fails to hold true. Now, the reason that that's interesting and useful to us is that this quantity here, the quadratic variation in an appropriate setting, actually does exist for Brownian motion and tells us a lot about Brownian paths. So here's the proposition. Let Bt be a Brownian motion on the interval from 0 up to t, real valued, say. If I let pi m be any sequence of interval partitions whose mesh goes to 0, then in fact, if I take the quadratic variation along those partitions, well, that's a random variable, to be clear. This means for each outcome omega, I take that quadratic variation with respect to that partition of the path bt as a function of t in that outcome omega. That sequence of random variables now converges. It converges to something. Actually, it converges to a constant, t. Now, that convergence is in the sense of L2, so that's why we have to be a little bit careful about what we mean by this limit existing in that case here. It's an L2 limit. But you can take any L2 limit and find a subsequence that will converge almost surely, and in fact, you can describe quite easily when that limit will exist here. If the meshes of the partitions decay fast enough that the sequence of meshes is summable, then you will actually get that these random variables, the quadratic variations of Brownian motion, converge almost surely to the constant t. And that is on your homework to prove. Now, I'll comment, by the way, that this is still not the strongest result. It turns out that if we assume that these partitions are nested, that is, pi m is contained in pi m plus 1, then you in fact get this almost sure convergence no matter how slowly the mesh tends to 0. You don't need this condition at all. But we won't need that result, and it's a little bit difficult to prove using some martingale methods, so I'll leave it to your outside reading if you want. And we'll satisfy ourselves for now with this result, that you can certainly find sequences of partitions, so that this sequence of random variables converges almost surely to the constant random variable t. Now, that has an interesting consequence which tells us a lot about how rough Brownian paths are. The result is that if p is less than 2, the p-variation of Brownian motion must be infinite. That is, we define the p-variation of Brownian motion to be a random variable, which for each outcome is the p-variation of the path t maps to bt of that outcome omega. That random variable takes value infinity on a probability 1 set of outcomes. That's the result here. But really what we're proving in this result here is that for any given continuous path, if its quadratic variation is well defined and non-zero, then its p-variation will be infinite for all p less than 2. So here's the idea. We'll fix some sequence of partitions that have mesh going to 0 fast enough that the meshes are summable. Then, as you're showing on your homework, it follows that the event that the random variable's quadratic variation of Brownian motion on those partitions converges to t is a probability 1 event. Now, let's take any outcome omega in that probability 1 event, and we'll suppose, for a contradiction, that the p-variation of that Brownian path is finite. Well, we can just compute now that the quadratic variation of that Brownian path along the partition pi m from the sequence we chose, that's just the square of the 2 variation along that path. So let's write out exactly what that means. It's the sum over all partition points in that partition of the increment btj of omega minus btj minus 1 of omega squared. And just to avoid lots of writing, let's denote this increment as delta j of omega. Now we can break up that square into two factors. This is the sum of delta j of omega to the 2, which we can write as delta j of omega to the 2 minus p times delta j of omega to the p. And here we're assuming that p is less than 2, which means that both of these are positive. Now I'd like to take this outside the sum. Of course, I can't just take it out because it depends on the sum parameter, but I can take out its maximum value. So this is less than or equal to the maximum over all ti in the partition pi m of delta I of omega to the 2 minus p times the sum over tj of delta j of omega to the p. Now this last sum here is exactly the p-variation to the pth power of the Brownian path along the partition pi m. And so that's less than or equal to the supremum over all partitions, which is the p-variation of the Brownian path. And our assumption for a contradiction here is that that is finite. Now what about this term here? Well, our Brownian path is a continuous path, and it is on a compact time interval, which means that it's in fact uniformly continuous. We're also taking a sequence of these partitions whose mesh tends to 0. Indeed, it tends to 0 fast enough that the sum is finite. So we'll see that that's going to make this very small. If we fix any epsilon, by the uniform continuity, we can find a uniform delta such that on any interval of width less than delta, the increment of the Brownian path is less than epsilon. Well, for all large M, the mesh of our partition is going to be less than that delta. Well, that means that in this maximum here, since the maximum partition width is less than delta, that means that for each one of these intervals from tk minus 1 up to tk, that's less than or equal to the partition mesh, which is delta. And so by uniform continuity, this maximum here will be less than epsilon to the 2 minus p. Now because 2 minus p is positive, this is arbitrarily small. And so what that shows us is that this is smaller than something arbitrarily small times some fixed finite constant, which means that this is arbitrarily small in the limit as well. So we've now shown that for any such path omega, the quadratic variation along the partitions pi m converge to 0. But of course that contradicts our result that in the set omega naught, those converge to t, which is not 0. And so we see that the p-variation is infinite for all p less than 2. It's actually true that it's infinite for p equal to 2 as well. Even though the quadratic variation is almost surely finite, the 2 variation, again defined in terms of the supremum over partitions instead of a limit of partition mesh going to 0, is infinite. That's a little harder to see, so we will content ourselves with the result for p less than 2 here. Now, what does that have to do with path regularity? Well, there's a nice connection between Hölder continuity and path p-variation. And here's the result. If alpha is bigger than 1/2, then on any compact time interval, the Brownian motion paths are not C alpha with probability 1. To be more precise, if we fix the event omega naught, like we did before, that the quadratic variation of the Brownian path along a sequence of partitions tends to t. For example, we can take any sequence here where the sum of the partition meshes converges as m goes to infinity. Then we know that that is a probability 1 event, and on that event, this path will not be C alpha for any alpha bigger than 1/2. We'll again prove that by contradiction. So let's assume that for any such omega in here, the Brownian path t maps to bt of omega is C alpha, which means that for any 2 times bt and bs in the interval from 0 up to t, the increment bt minus bs is less than or equal to some constant, which can depend on omega, times s minus t to the alpha. Well, now we'll do much the same thing we did in the previous slide, and we'll write down the formula for the quadratic variation along the partition pi m. That's here. And using this inequality here, we get that that sum is less than or equal to that constant k squared times the sum over all the partition points of tj minus 1 to the 2 alpha. And now we'll break that up as that to the 2 alpha minus 1 times that to the 1, which we can do without any trouble because 2 alpha minus 1, by assumption, is positive. Now we bound the terms in here by their maximum. And all we're left with is the sum over partition points of tj minus 1. But of course we know that that telescoping sum is just equal to capital T. Now this maximum here is exactly the partition mesh. And so what we've shown is that this is less than or equal to a constant times the mesh to some positive power. And that, of course, goes to 0 as m goes to infinity, which contradicts the fact that the quadratic variation, as you've shown in your homework, actually converges to t for all omega in here. And so that completes the proof that the Brownian paths are not C alpha on this probability 1 event. Now again, this result also holds true with alpha equal to 1/2. Brownian paths are almost surely not C 1/2, although they are C alpha for every alpha less than 1/2, as we've already shown. This is true on any interval from 0 up to t, and if you modify things a little bit, you could prove it on any interval from s up to t, if you like, no matter how small or big that interval is, which suggests that this is also locally true. And that's the case, although it's an even stronger result. And to do that, we need to first define what it means to be locally Hölder continuous. That's where we'll go next.